Everything around us is in constant motion, constantly changing. But how do we actually measure that change? Not over an hour or even a minute, but in a single fleeting instant. Well, in this explainer, we're going to dive into differentiation, the amazing mathematical tool that lets us pinpoint the science of change itself.
Okay, let's start with our really simple question. How fast is a car going right now? Figuring out its average speed is easy, right? It's just the total distance divided by the total time. But what about the exact speed on your speedometer at this very second? That's an instantaneous rate of change, and solving that little puzzle is exactly what calculus is all about.
And to answer that question, we need a special tool. Calculus. Yep, it's that branch of math specifically built to study motion, growth, and how things change over time. The specific part we're going to focus on today, differential calculus, is the key to unlocking those instantaneous rates. So here's our game plan. We'll start with the why, then we'll define the single most important concept in all of this, the derivative. From there, we'll start building our toolkit with some basic and then some more advanced rules. And finally, we'll put it all to work on a real-world problem. Sound good? All right, let's jump right in. We're starting with the science of change. The best way to think about differentiation is like putting a single moment in time under a powerful mathematical microscope. So this brings us to the absolute heart of the matter, the derivative. Seriously, if you remember only one thing from this entire explainer, make it this. The derivative gives us the language we need to talk about instantaneous change with total precision. So what is it really? Well, a derivative measures how fast a function is changing at one specific point. Now, geometrically, it's even easier to picture. Imagine a curve is a roller coaster track. The derivative at any point is just the steepness of the track at that exact spot. It's the slope of a line that just kisses the curve at that one single point. Now, you're going to see derivatives written in a few different ways. You'll see f prime of x, dy dx, but don't let all these different labels fool you. They all mean the exact same thing. They're just different nicknames for the same core idea. Find the derivative. Okay, so we know what a derivative is, but how do we actually find one? Thankfully, we don't have to reinvent the wheel every single time. We have a set of really powerful shortcuts, or rules. Let's start building our toolkit with the basics. Our very first tool is probably the easiest one you'll ever learn, the constant rule. The logic here is just beautifully simple. A constant is a number that, by definition, doesn't change. So what's its rate of change going to be? Yep, it's 0. The derivative of any constant number, whether it's 7 or 7 million, is always 0. If nothing is changing, the rate of change is 0. It's as simple as that. Next up is the absolute workhorse of differentiation, the power rule. You are going to use this one all the time. It is the key to handling any variable raised to a power, which is totally fundamental for everything from physics to economics. The process is a simple two-step dance. First, you bring the original exponent down to the front as a multiplier. Second, you just subtract 1 from that original exponent. So, if you look at our example, x to the 4th becomes 4 times x to the 3rd. See? Easy. But what happens when you have a function with multiple parts added or subtracted together? Well, that's where the sum and difference rule comes to the rescue. It basically lets us break a big problem down into smaller, manageable pieces and just handle each one separately. Okay, let's walk through this example together. We just apply our rules to each part one by one. The derivative of x cubed? That's 3x squared, using our power rule. The derivative of 4x is just 4. And the derivative of that constant, -9, is 0. We just combine those results, and bam! The final answer is 3x squared plus 4. All right, we've got the basics down cold. But what happens when functions get a little messier? Like when they're multiplied, divided, or even nested inside one another? For that, we need to add a few more advanced tools to our kit. So for multiplication, we have the product rule. For division, we use the quotient rule. Now take a second and just look at their structure. They look pretty similar, right? But the quotient rule has two super important differences. It uses subtraction instead of addition, and you have to divide the whole thing by the original bottom function squared. Those details are absolutely crucial to remember. And now for my personal favorite, the chain rule. This is the one we use for what we call composite functions. Basically, a function that's living inside another function. The best way to think about it is like a set of those nested Russian dolls. The trick is to work from the outside in. First, you take the derivative of the outer function, and you leave the inner function completely untouched. Then, you multiply that result by the derivative of the inner function. So for our example here, the derivative of the outside part is 4 times 3x plus 2 cubed. Then, the derivative of the inside part, 3x plus 2, is just 3. Multiply them together, and you get 12 times 3x plus 2 cubed. So, we've built this entire toolkit of rules. That's great and all, but what's the point? Let's connect all of this back to the real world and see why this stuff is so incredibly useful.
So where do we actually see this in action? It's everywhere. We use it to calculate the velocity of a spacecraft, to pinpoint the exact moment of maximum profit for a company, to design the smooth, beautiful curves you see in animated movies, and even to train the artificial intelligence that powers so much of our modern world. Okay, let's tackle a real problem. This function you see here, s of t, tells us an object's exact position at any given time t. So the big question is, how can we use this to figure out its velocity at any given instant?
Well, just remember, velocity is simply the rate of change of position. So to find the velocity, all we have to do is take the derivative of our position function. Using the rules we just learned, the derivative is 3t squared minus 10t plus 2. And that new function we just made, that's our key. It's a powerful tool that can tell us the object's exact velocity at any instant we choose.
This quote really says it all, doesn't it? It perfectly summarizes our journey today. Differentiation isn't just some abstract math exercise. It's a fundamental skill for describing, understanding, and solving problems in a world that is completely defined by change. So we've spent this entire explainer learning how to break a function down to find its rate of change. But that leaves us with a really fascinating question. What if we already know the rate of change and we want to work backward to find the original function? What if we want to build it back up?